All right, hey everybody, back for the second half of this last problem here. I got a little diagram sketched here to show you where we came from. We started with a square. We showed that OABC is a square. We found this vector OB and found its midpoint M, so it should be centered in the middle of that square. It's the intersection of the two diagonals, OB and AC. All right, and then we projected this line L out of M toward D, right? Toward D. And D is the point we're going to be trying to find. Okay, so let's recall what L was. L was, I'm going to write this in yellow. I don't know if this will show up very well for you, but we started at M, and M we found to equal 3, negative root 6, and root 3. And then it heads in the direction of the normal, which we found to be 0, 1, and root 2. Okay, so in parametric form, I'm going to write L in parametric form now. X equals 3, Y equals negative root 6 plus lambda, and Z equals root 3 plus lambda root 2. Okay, what we want to do is find the coordinates of D, the point of intersection of line L, with the plane whose equation is y equals 0. Okay, so it's some plane whose equation is simply y equals 0. So if I were to write out the equation of this plane, y equals 0, I'm going to substitute in for y the y component of L, right? So I'm going to substitute in negative root 6 plus lambda, and I'm going to solve for lambda, which would be root 6. So if lambda is root 6, that means root 6 steps along the normal in the direction of line L gets us to point D. So what I'll do with this lambda value of root 6 is I'll plug it back in, so that won't change anything with regards to the x coordinate. The y coordinate will be negative root 6 plus root 6, which makes sense, seeing that y will be 0 on the plane where y equals 0. And z will equal root 3 plus root 6 times root 2, which is root 12, which actually comes out to be 2 root 3. So we would get 3 root 3. Therefore, the coordinates for D, I guess I don't need the equal, the coordinates for D would be 3, 0, 3 root 3. Okay, so find the coordinates of E, the reflection of the point D in the plane pi. So let's draw pi again. Here's pi, O, A, B, C. Here's M. And up here we have point D. And here's line L. And of course, line L is perpendicular to that plane. And then we have point E. Well, where is point E? Point E is equidistant from the plane, but on the opposite side of the plane. So if I head along L toward D, it took me lambda equals root 6 steps, or you could think of that as time as well, although in this case it's not a great idea. So if I had the opposite direction, the same distance, then lambda should equal the opposite of what it did to get to D. So to get to E, we would plug into the same equation, right, for line L, because E will be on line L. But now we're going to plug in negative root 6 for lambda instead of positive root 6. So I'm going to plug in a negative root 6 for lambda and a negative root 6 for lambda. So the points for E will be still 3, negative 2 root 6, and let's see, I don't want to screw up this math here. This would be, oops, that should be a root 3 here. So that would be a root 3 plus negative 2 root 3, which would be a negative root 3. And there I've got E, okay, which would be on the opposite side of the plane, equidistant from the plane, and along line L. All right, let's see what the last part of this question has in store for us. Okay, find the angle ODA. All right, so let's sketch this out one more time. I'm going to try to give it a little bit of depth. It's not going to be perfect, but that's okay. So I got O, got A, got B, got C, got M, I got D, I got E. I'm going to try to give this some perspective. Okay, and I've got that. Ooh, that's no good. Okay, this is kind of cool looking. It says find the angle ODA. All right, so it's kind of hard for me to see, but it's going to be back here. It's going to be that angle there, okay, which should be the same as this angle here, okay. And actually, these should all be the same angle, based on the fact that the square in the middle and all that good stuff, and D is directly over the midpoint of that square, or the center of that square. So I'm gonna sketch a few things out, and I'll come back and explain. I decided not to sketch them out and just to kind of walk through it here, but I'm going to draw this triangle. I'm going to flip it here. So it'd be this triangle here, which would be, let's go like this, O and A and D. So I want this angle there. All right, so how do I find that angle? Well, the cosine of that angle, we'll call it theta, is going to be equal to the dot product of DO times the dot product of DA, excuse me, times DA, or dotted with DA, over the magnitude times the magnitude. Okay, so I did the calculations on the side here. So you'll have to refer back to DO and DA and all that good stuff for dot product and magnitude. But for the dot product, I got 18, which tells me it's an acute angle, which makes sense, right? If it's positive, it's going to be acute. If the dot product is positive, that is. The magnitude of DO came out to be root 36. That's root 36. And the magnitude of DA comes out to be the same, root 36. So root 36 times root 36 is 36, and 18 over 36 is equal to a half. And the cosine of what angle gives me a half is 60 degrees. Okay, so for part 1, theta is 60 degrees. Now in part 2, it says state what this tells you about this solid. And this is going back a ways, and maybe you didn't even ever visit this. But this solid OA BC DE is what's called a regular octahedron. Okay, so it's got 8 faces. It's got 8 faces, and all of them are equilateral triangles. So it's got 8 faces, all of which are equilateral triangles. It's pretty cool. And that's it. That's problem 12. So that wraps up week number 5. I hope it went well. I know that we got cut off due to the whole coronavirus situation. But again, shoot me questions if you got them, and I'd be more than willing to meet with you online and talk it through. All right, have a great day.